So when we have binary relations as opposed to arbitrary relations, there are lots of things that we could say about them, and there are lots of different types that tell us a lot about the structure of the underlying problems that we model using that relation in many cases. Here's some example. So we call a binary relation reflexive if every element is related to itself. So if you draw a graph of that relation, you will draw a loop relation to itself on every single vertex, on every single number here. For example, your relation 1, 1, 2, 2, and 1, 1, 2 is reflexive because 1, 1 is there, 2, 2 is there, and there are no other elements. The relation on any set that is a quality relation, x equals y, is going to be reflexive because everything is related to itself. And in this case, it's not even related to anything else, but everything is related to itself. But if you take x less than y, strictly less than y, that's not going to be reflexive. It's actually more than not just not being reflexive, because here nothing relates to itself. We do have a name for that, an anti-reflexive relation. So a binary relation is anti-reflexive if none of the elements is related to itself. So you see, in both reflexive and anti-reflexive, we use a universal quantifier. We say everything is related to itself, or everything is not related to itself. Nothing is related to itself. So an example of something that's anti-reflexive is less than, or a relation on the set 1, 2, which only contains a pair 1, 2. It could also contain the pair 2, 1, that doesn't matter, but it shouldn't really contain 1, 1 or 2, 2. Adding either one of them in, so if you have a relation that only has 1, 1, but not 2, 2, will make it not anti-reflexive, but also not reflexive. So here are some more examples. If you have a relation x plus 1 equals y, that's anti-reflexive because if you add 1 to any number, you're not going to get that number back. An example of yet another relation that's not reflexive is a parent. It's not just not reflexive, it's anti-reflexive because nobody is their own parent. And again, most of relations out there are neither reflexive nor anti-reflexive. Some elements are related to themselves, others aren't, but the ones that are reflexive and the ones that are anti-reflexive are pretty useful, and some of the big common ones are in one of those categories. So another property of relations is about what is a relation not to, of element to itself, but of an element to other elements. And one of them is a symmetry. So a binary relation is symmetric if every time you have x related to y, y also relates back to x. So every time you draw an arrow one way, you need to draw an arrow the other way. So the relation that we had before, 1 to 2, that was not symmetric because we could go from 1 to 2, but we could not go from 2 back to 1. Well, if nothing relates to nothing else, it's symmetric because every time, as in none of the times where you have a relation from A to B, you have a relation back. That would be vacuously true. So the relation R8 drawn here is symmetric because you could go from 1 to 2 and you could also go from 2 to 1. It's not reflexive, it's not anti-reflexive because 1 has a loop and 2 doesn't, but it is symmetric. So being reflexive and being symmetric are two properties that don't really interact with each other. Something can be symmetric, but reflexive symmetric and anti-reflexive symmetric, and neither, and it's fine. One of the classic examples of symmetric relation is the mod, congruence mod a number relation. If the number x and the number y have the same remainder mod 3, then, well, y and x also have the same remainder mod 3. In other terms, when we talk about symmetric relation, you could think about Facebook. If you're somebody's friend, they're also your friend. But it doesn't necessarily hold for other, well, relations as in following relation. You could follow somebody, but they may not be following you back. So being a friend, in this case, is symmetric. Following, in this case, is not symmetric. Just like we had an anti-reflexive relation, we could have an anti-symmetric relation. And again, we have a universal quantifier here that no matter what x and y we take, if x is related to y, in this case, that means that y is not related to x. It cannot be. And if you want to think of a specific example, think of a parent relation. If x is a parent of y, there is no way y can be a parent of x. If x is strictly less than y, or even less than or equal than y, there is no way y can be less than or equal to x unless they're equal. Equal is okay. And there is a very strange relation which is both symmetric and anti-symmetric, that relation which didn't have anything related to anything else, where every element was just related to itself, the R2 relation. It's both symmetric and anti-symmetric because in both cases the condition was vacuously true. If x is related to y, then, well, okay. If nothing is related to nothing else, then we are done. The whole thing is true. Finally, one more property that you're going to hear a lot about when you're doing graphs and when you're doing algorithm is transitivity. A relation is transitive if you can kind of transit through it, so to say. If whenever you could get from x to y, if x and y is a pair in the relation, and you could get from y to z, you could get from x to z. So here is where visualization as graphs like this becomes really useful, because you could talk about walking on a graph. Say I start at vertex number 3, I walk over to vertex number 1, from there I walk over to vertex number 2, so I made my way to vertex number 2. If the relation is transitive, I didn't need to go through 1, I could have just gone to 2 directly. And if you want to think of remembering the name, imagine that you are taking a bus in some city, say in St. John's, and you are trying to get from downtown to the airport. You can get from downtown to the airport by bus because you could go to MAN, then switch from bus number 10 to bus number, whatever it is, 14, and get to the airport. So the relation of getting there by bus is transitive. If you could get from point A to point B and from point B to point C, you could get from point A to point C. I'm not talking about bus connections. I'm just talking about getting there eventually. But if you just talk about the relation of getting there by bus without transiting, without changing buses, then getting somewhere by a single bus is not transitive. I need only one bus to get from downtown to MAN. I can get from MAN to the airport, again, by only taking one bus. That doesn't mean that there is a bus that takes me directly from downtown to the airport. I sure wish they were.